All right,
as I promised, we'll restart with the last of the important properties of synchrotron radiation from storage rings, that is coherence. And coherence is now becoming very important, and we shall see why. But let me start by seeing what is it. So let me make a simple comparison, because we can use a classical analogy once again in order to understand what's going on. That is, let's take a screen with two slits, a fluorescent screen, and we would like to get some kind of diffraction with a fluorescent screen. Now, let me start from a light bulb. A light bulb does not give you diffraction, okay? Why? Because there is no coherence. Now we take a laser, and the laser instead is coherent and gives you diffraction. So you can start understanding what is coherence, okay? In one case, there is coherence. In the other case, there is no coherence. And so by simplifying things, we can say that basically coherence is that property that allows the radiation to produce detectable wave-like effects like interference or diffraction, okay? And you can remember from everyday life that in some cases we see a wonderful diffraction colors, even from sunlight. Okay, that's an interesting topic on its own, okay? But this gives you the difference between coherence or no coherence. And so synchronous radiation sources have a very high level of coherence, which is being used more and more for applications, notably in radiology. We have seen the first two talks some of these fantastic pictures, okay? They're looking at very small details, and that's becoming extremely important, and it is strictly related to coherence. So in order to understand what is coherence, we can use any kind of wave-like effect. Like, for example, let's take a pinhole and let's produce a diffraction pattern. Now, let me start from an extreme case. That is a point source, a source with no dimension, no physical dimensions, that emits only one wavelength. Now, in this case, you are always getting a diffraction pattern because there is full coherence. But now this is a little bit of an unrealistic case. It is an idealized source. So we would like to make the things a little more realistic by taking something which either does not have only one wavelength or has a finite size. Let me start from the multiple wavelengths. And what we can see that actually this is a situation in which each wavelength is producing a diffraction pattern. What you really see is the overlap of all the patterns, and this broadens the fringes, and so we may not be able anymore to see a diffraction pattern. Now, if you do, then you can say that there is what is called time or longitudinal coherence, time coherence. Now, let me now relax the other condition. Instead of having a point source, let's have a source with a finite dimension. Each point of the source is producing a diffraction pattern, and once again, this can broaden things to the point that you don't see a pattern anymore. If you do, there is spatial coherence. So now we would like to elaborate a little bit in order to understand a little more what are the conditions for having the spatial and or time coherence. Let me start from the time coherence. Now, suppose that we are looking at the two diffraction patterns that are produced by two different wavelengths. Now, let's combine them together, and you could get a blob. So you can get something which has no diffraction pattern visible anymore, and so there is no coherence anymore. The question then is, what is the condition to still see a fringe? The calculations is very simple, so I will not go into the details here, but basically you take the distance between the fringes from elementary optics, and this is the formula. and then you blur the wavelengths in order to get a band. And then you can see that actually the condition to see the pattern is that the blurring is smaller than the distance itself. And therefore, by taking this simple formula, you get delta lambda over lambda smaller than 1. Okay? And so this is the condition for time coherence. Quite often, when you're looking at imaging, then you find that actually you use a parameter in order to express the same concept, which is the coherence length, which is defined in this way, and therefore the time coherence requires that the coherence length is bigger than the wavelength. So this is the simple approach to time coherence. Now let me go now to spatial coherence. Let's take the emissions from different points in the source, and then the combination that can give you just a blob. What are the conditions to still see a pattern? Once again, you can repeat a simple approach, and you can see that the condition is given by a comparison of all the effects of different points in the source with the distance between fringes, and you get very easily to this condition for spatial coherence. Quite often, the same kind of concept is presented in a slightly different way, which is also very powerful, because what you can note is that not the entire emission is contributing to the diffraction pattern. So much of the emission is lost and cannot contribute to this wave-like phenomenon for the simple fact that it is not going through the pinhole. So only a fraction of the emission, the fraction that corresponds to this solid angle, can contribute to diffraction. So if you are taking this, then you find that the emission is that is going to the pinhole, through the pinhole, and therefore it is the emission in the solid angle delta square over d square. And by putting together with this the condition for spatial coherence, you are getting this result, which corresponds to a fraction of the total emission equal to this and therefore to this. This is what is called the coherent power factor, and it is the most effective way to measure spatial coherence because it puts together not only the dimension of the source, but also the fact that there is an angular spread of the emission, and therefore much of the emission or a part of the emission is lost as far as producing a visible diffraction pattern is concerned. Okay, and so now we can specialize our question about the coherence of synchrotron radiation by asking, are synchrotron radiation sources spatially coherent? That is, do they have a high coherent power? And the answer is yes, yes, yes. Why so? Because basically they can produce a small cross-section, they can produce a small angular divergence. They are the parameters that are in the denominator of the coherent power factor, and therefore they can boost the factor and boost the spatial coherence. Now, we must realize that, however, there is a bemol in this result. That is, if you're looking at lambda square in the coherent power factor, this is a killer, because if lambda becomes very small, as it is for X-rays, then the coherent power factor is negatively affected. That is why, if you're looking at the history of things that have been realized with diffraction or interference and so on, we find experiments of this kind 3 centuries ago, okay, because they were done with the visible light that has a much longer wavelengths than X-rays. With X-rays, we never bothered about spatial coherence until the arrival of synchrotron radiation, and even then, it took us some time in order to realize that there was indeed a high coherent power. And so now the other point to be noted is that the geometric factors are present in the brightness as in the coherent power factor. So we have been struggling for decades to increase the brightness, notably by improving the geometric characteristics of the source, okay, for example, using relativity to decrease omega. And we got a bonus, that is, the same factors are also increasing coherence, so we got high brightness and high coherence. Is this important? Yes, because this is what you can do by using coherent synchrotron radiation. These are some examples of images that are produced by coherence. And you can see that there are very small details. You can go to very, very minute characteristics. And so you are opening up a completely new chapter in radiology, which is still the biggest application of the biggest application of X-rays. Now, I conclude in this way this part of my presentation by making a short summary. These are the properties that we explain, use this very single approach. You can expand that, you can go into other properties, but basically the message is that you can make synchrotron radiation very simple. Okay, now, having concluded this part, now the question is, what are we going to do with synchrotron radiation? How can we exploit its characteristics? In other words, what are the interactions with matter that we can use for practical experiments? Now, before going into the details, let me emphasize that there is not a single answer, because there are many different kinds of interactions between X-rays and atoms or molecules or solids. Each one of these physical mechanisms is exploited by one or more experimental techniques. So we are talking about a huge variety of possible applications. So synchrotron sources, we must stress, are not specialized tools. They're not accelerators in the sense of elementary particle physics, in which an accelerator is developed for one single experiment. They are facilities that are used for many different experiments, different between them in parallel, and this, of course, has the result of spreading the cost. Now, today, I don't have the time to go into too many of these, and so I will concentrate on a subset that is the subset of the techniques that are mostly used for solid-state experiments. So, let me start with the interaction of X-rays with solids, okay, giving a general picture and a bit of a formal background. Don't be scared, it's not going to be complicated formalism. So, we take a solid, we take a wave. The wave arises at the interface between vacuum and the solid, okay, and until then it moves at a constant speed, but then there is something happening. There is refraction. That is, there is a change in direction that occurs at the interface. Furthermore, as the wave propagates in the solid, it can be progressively absorbed. You can see here the amplitude decreases. And also, it can be subject to what is called phase effect, such as interference or diffraction. So we have diffraction, we have refraction, we have absorption, and we have phase effects. Now, from the formal point of view, all such phenomena can actually be treated with one single parameter, what is called the complex refractive index. Let me briefly introduce it, okay? Let's take a wave function in vacuum. Okay, we can propose a sine function like this, but actually from the point of view of mathematics, it is more effective instead of using a sine function to use a imaginary exponential like this with an imaginary exponent. Now, this is the wave in vacuum, and we must distinguish between its amplitude and this factor, which is called the phase. Now, when the wave gets into a solid, then the change is that n becomes, k becomes nk, where n is the refractive index, but it is not a refractive index of elementary optics. It becomes a complex quantity. So let's plug this complex quantity into this exponent, and then we can see that we have actually two aspects. First of all, there is this factor a multiplied by the exponential of the imaginary part of the refractive index times k times r. Now, this is no longer an imaginary exponent, so it's not an oscillating function, but it is a decreasing exponential function because there is a minus factor here. And so this is very simply absorption. And now we are taking the other part, and we can see here that the real part of the refractive index is determining the phase, and therefore is giving you what we have been calling the phase effects. Now, in the interactions in the techniques of synchrotron radiation, the phenomena can be absorption or phase effects, or actually a combination of them. Okay, and we shall see now some of the most important examples. So now, before leaving this formal part, let me mention that the real and imaginary parts of the complex refractive index have some general properties. For X-rays, the imaginary part, the one that gives absorption, is very weak. And in fact, we know that X-rays are going through bodies. You can use radiographs for medical diagnostics and so on. The real part is very close to 1, which is no refraction, and therefore refraction is very weak. So for X-rays, absorption and refraction are both weak phenomena. The other important point is that the two factors, that is the imaginary part and the real part of the refractive index, are not independent, but they are linked by the so-called Kramers-Kronig equation. Don't be scared, we are not going into these complicated equations and so on. Let me just tell you that you can derive this from very general conditions, like the condition of cause and effect and so on. Okay, but the net result is that the two kinds of phenomena are not completely separated, but they are linked. In fact, you can see that in everyday life. If you want to build a mirror, yes, you want to have reflection, but you also get absorption. In fact, you don't take just a glass, you get a metal coating in order to get absorption. So the two things are related. And in general terms, when there is something, if you take a plot of the two parts of the refractive index, you find, as a function of the photon energy, you find if there is something that happened to one, then there is something happening also to the other. These are the general properties. Okay, so much for the minimum of formal background. And now let me go to the oldest and still, as I mentioned, the most widespread use of X-rays, that is the imaging. Okay. Now, imaging is based both on absorption and on phase effects. But if you're looking at the whole history of X-rays, you find that for almost a century, we only used absorption. Okay, we have images, radiographs that are caused by absorption. However, this was because we didn't have coherence. And so there was no point in thinking about phase effects. Now there is coherence, and so we start thinking about using phase contrast, that is the mechanism in imaging that are related to the phase effects. Are they complicated? Yes, they are, okay? But once again, we can understand the simple facts by using a simple classical analogy, that is, seeing a glass of wine. For those that are not wine drinkers, they can take a glass of anything colored, because what you can see is that there are actually two ways in which we see the glass of wine. First of all, well, there is an absorption and non-scattering of different wavelengths. And so this gives you the color. And so you get a color red. But this is not all, because you also see the edges of the glass. The glass is not absorbing. It is not, so it is a phenomenon that goes for a transparent glass, so it is not related to absorption. There is instead phenomena like refraction or scattering that are related to the phase, and this makes the edge visible. Likewise, if you are looking back at the images that I proposed you in a short time ago, then you realize that the quality, the fantastic quality of these images is coming primarily from edges that become very visible, okay? And so, and this is possible because of the spatial coherence, because in order to get these effects, you need to have directionality of the X-rays, and therefore small angular divergence and high, strong angular collimation. So that is why spatial coherence gets into the scene. You can understand this phenomena in a very simple way. Let me just propose to you this possible simple model, but I will not go into the details. I'd like you to look at that if you're interested. But basically, in this way, you can understand the formation of fringes in the images like that. This is the predicted couple of Darner bright fringes, and this is a real experiment. Okay, so we can now go into what is that you can do by using phase contrast imaging. Well, some time ago, we became interested in what I would like to call the miracle of fireflies, okay? That's a wonderful phenomenon, not only from the point of view of the beauty, but also from the technical point of view. This is a study that we performed a few years ago of the organ that is responsible for the emission of light. And you can see it's a very complex organ with the minute details. Without having the fantastic resolution of phase contrast imaging, you cannot detect all these details. But with phase contrast, you can do it. And therefore, you can see even the smallest possible tubes. And this allows you to have a quantitative analysis of the possible chemical phenomena that are responsible for the emission of light. In this way, you can discriminate between them and explore this fantastic effect. You know that if you try to reproduce the same phenomenon on a plane, you would crash the plane instantaneously because the emission would be too much energy. And now let me give you to another example. The other example is the study of neurons in a brain. You can see here that with the resolution we get, it is possible to see not only the single neuron cells, but also the connection. And so this led us recently to a coalition of synchrotron radiation sources and high-performance computing centers, mostly in the Far East, but also in other regions. For example, Sesame is part of this coalition now. And the objective is rather ambitious. It is to explore a full, oops, excuse me, Okay, let me skip to the next transparency because the video is causing problems. Okay. So just to conclude the previous part, the ambition of this coalition is to map one full human brain on a scale of a few years. And now let me go to another technique that is the case of X-ray absorption spectra of solids, which have...
Sorry to interrupt you, Professor. We cannot see your slides.
Oh, excuse me just a moment. Okay.
Yes, now we see, but not in presentation mode.
Yes, indeed. I'm going into the presentation mode. Yeah, the video sabotage in some way. All right.
Okay.
Okay, so we are talking about core level edges in absorption spectra. Okay, the question is what is causing these edges and how we can use it. To do that, I like to propose to you the distribution of energies in a solid. And you know that in the solid there is going to be electrons in the valence band, there is going to be electrons in core levels, and there is going to be a gap, a forbidden gap, and an empty conduction band. In order to have absorption of X-rays, you need to have a transition from a state full of one electron, for example, to an empty state. So we send a photon and we promote the electron to the conduction band. Now you can see that a transition from the core level to the valence band cannot take place because these states are occupied. Okay, they do not accept additional electrons. So we must go into this. And this explains the core level edge, because basically you get the edge when you have an energy that corresponds exactly to the distance between the core level and the bottom of the gap. So that is the cause of a core level edge. And that's a very important characteristic because in this way you can explore the solid and understand a lot about its characteristics. So, for example, the core levels are the label of a specific chemical elements, and therefore if you see a core level edge, you reveal the presence of the chemical element. And also, you can provide more information about the chemical status and more. In particular, with synchrotron radiation, it is quite popular to use the technique that is called EXAFS, extended X-ray absorption fine structure. You can see here a more detailed picture of an edge. So you see the edge, but then you see that above the edge, there is actually some structure. There is a fine structure that extends over a rather large photon energy range. So what can you learn from this kind of EXAFs? Well, suppose that we are looking at a crystal, and we are looking at the atoms in the crystal, and we are now zooming on one specific atom, which is where the absorption of X-rays takes place. So let's zoom, and we focus on one photon absorbing atom and one of the atoms that is in the neighborhood of this one. We send a photon, the photon excites an electron, and there is an electron wave. This is an electron wave that is emanating from the absorbing atom and going into the neighbor atom, and there is going to be backscattered. So what is important in order to see how much absorption there is the interference between the outgoing wave and the backscattered wave, which could be positive or negative, depending on several parameters. For example, the energy of the electrons and therefore the energy of the photons, but also this distance, d. Okay, and so it is this interference between the two waves that gives you the maxima and minima in the oscillations that are called XRs. And making a simple history, a complicated history simple, you can realize that you can extract from these oscillations the value of this distance and therefore get a very valuable piece of information about the neighborhood of a specific atomic species. Okay, now what happens to the energy of the X-ray photons that are absorbed by a solid? Well, there are several mechanisms by which you can decay, but one possibility is to stimulate the emission of secondary X-rays. Let's see what's going on. This is the X-ray from the synchrotron, and then you get emission of X-rays. And this is the energy picture. Once again, we have the core levels, we have the valence band, you have a photon coming, excitation. This produces an unstable situation because there is an empty state here and there are electrons available at higher energies. So what could happen is that one of the electrons goes down and emits an X-ray photon. Now, this is characteristic of the position of the core levels. And so once again, by looking at this emission of X-rays, you can measure the photon energy and you can understand what are the elements. So it is a tool for chemical analysis, which is in fact very widely used. All right. Next chapter, actually, we are getting to a class of techniques that are primarily based on absorption, and they are one of the most widespread used kind of techniques with synchrotron radiation sources. So actually, the photoemission is based on the photoelectric effect. Okay, let's see what it is. All right, you get photon emission of an electron, which becomes a photoelectron. Okay, and this actually, if you're looking at what are the mechanisms that are producing absorption, then you find that this phenomenon, the photoelectric effect, is the most important one in the typical range of wavelengths of synchrotron light. Okay, and this kind of phenomenon can be used in order to explore the energies of electrons that are engaged in chemical bonds. So we go from an atom to a solid, and therefore we change the spectrum of energies for the electrons. Okay, this will be the atom in vacuum. This is the atom in the solid. We would like very much to be able to explore this energy spectrum. But the problem is that if the electron is in the solid, we cannot capture it and we cannot look at its properties. And so that is why the photoelectric effect is important, because it frees the electron and now you can capture the electron and you can measure its properties. And in fact, what you can realize is that the photoelectric effect basically takes the distribution and it kicks up the distribution by an energy equal to the energy of the photon. So now this is in vacuum. It is something you can measure and you can retrieve from it by subtracting the photon energy. You can retrieve the objective, which is to study the distribution of energies of electrons in the solid. Can this be used? Of course. I mean, in fact, for many years, it was the main techniques for synchrotron radiation experiments. And just to give you one example, this is, once again, the spectrum of energies for electrons in a solid. We find core electrons and valence electrons, and then both these will be the conduction band and so on. Now, when you are looking at the photoelectric effect, then photoelectric effect is extracting electrons from either the core levels or the valence band. And if you are measuring the number of photoelectrons that are captured, you can see that you're getting a curve like this. This is the energy corrected by the photon energy, and this is the number of captured photoelectrons. Normally, this is shown rotated in this way. Now, folks, I like to tell you that I was there when this technique was first developed using synchrotron radiation. And I was a young fellow. I mean, I had 25 or 26 years, and it was a very, very nice experience. Why so? Because up until then, as a student, I've been looking at the quantum properties of electrons in the books. I didn't have any way to look at them directly. So I knew that there should be atomic states, and therefore the formation of core levels in a solid, and then the valence band, the formation of chemical bonds. All this was very nice, but it was very bookish. By just looking at spectra of this kind, I had a revolution in my mind, because my bookish quantum notions were transformed into a tangible reality. And it was wonderful. And it is not all, because for the mission, you can also study other electronic properties like superconductivity. Now, if you're looking at the energy aspect of superconductivity, you know that if you're looking at the distribution in energy of the electrons, so this is the energy. When you go from the normal state in black to the red state, that is a superconducting state, you are forming a gap right at the edge of the distribution for the normal state, which is a superconducting gap. This was invented or discovered many years ago, but it was essentially impossible to look at the gap because it was too small to see it with photon emission. So with photon emission, the resolution was not there, and therefore we just blurred everything. But then with the advent of synchrotron radiation, with ultra bright synchrotron radiation and the high temperature superconductors, the resolution became reasonable, and we could start seeing the superconducting gap directly. And this is now one of the main techniques to study high temperature superconductivity. So much about photon emission, and now we are almost at the end of this part of the presentation, because I would like to keep a few minutes for the bonus, that is the X-ray free electron lasers. We are going to talk briefly about the techniques that are based on phase effects, okay? Of which the most important one, or the main one, elastic X-ray scattering. Elastic means that there is no loss of energy, so there is no absorption. We are talking about a phase effect. So if you're taking a microscopic object like an atom, or excuse me, a molecule or a virus, okay, then we would like to understand what is the microscopic structure, that is the electronic charge distribution. So this is the target of this kind of experiments. And what we can do is to send X-rays into the system, and there will be scattering, elastic scattering. So there will be a direction of the incoming X-rays with a K vector for the wave, and there is the scattered K wave. And the general theory is quite simple. We are not going to go through it, but let me say that it is not extremely difficult. And you can demonstrate that if you define the scattering vector as the difference between the K vectors, then the scatter wave is proportional to this. And for people that know mathematics, they can recognize easily that this is nothing else but the Fourier transform of the function f. So the scattering phenomena essentially is a practical Fourier transform for the charge distribution that we would like to determine. How can we do that? Well, we can take the inverse Fourier transform. Okay, this is the inverse Fourier transform, and therefore the f, the charge distribution, which we would like to determine, is essentially the inverse Fourier transform of the scattered X-rays. That sounds wonderful, because now if you want then to understand what is a microscopic charge distribution, you perform a scattering experiment. You get an unknown object, send X-rays, get a scattering, get a scattered pattern, and then you make an inverse Fourier transform, and bam, you have the initial charge distribution. Well, bam to a certain extent, because actually it's a little more complicated than this, for a number of reasons, but primarily for what is called the phase problem. What is the phase problem? Well, basically is something related to the fact that when we are performing a scattering experiment, we are not measuring a wave. A wave is an electromagnetic field. We are not measuring the wave, we are measuring an intensity, which is the square of the intensity. And therefore, this interferes with the phase in a way that is absolutely not easy to solve. But nevertheless, this problem has been attacked and solved in many cases using synchrotron radiation and its properties. And so this is giving us now a number of possible different techniques. And so one must make a distinction in this kind of experiments between the imaginary case and the real case. In a realistic experiment, you're not going to get scattered X-rays in all directions because your detector is not extremely large. So you're going to capture only a portion of the entire distribution, and therefore you must understand what is the consequence on that on the techniques that they're going to implement. There are two possibilities. If you use a small detector, then the Fourier transform is only giving you the general shape of the object. But if you are getting a big detector, and therefore you can go also to large angles, then you can go into the details. So basically, a small angle scattering is very useful if you want to have a first look, and then you go into refinement. This, for example, is what has been used to solve the structure of the COVID virus. Now, crystallography. This technique, as we have seen in the case of, indeed, the COVID virus, can be extremely important in order to understand the microscopic structure of things like viruses or proteins in general and so on. But there is a huge problem. The huge problem is that X-rays can create defects, can damage the molecules or the virus. And therefore, you can have a distorted kind of result. The problem is now being solved by performing the experiment not on a single molecule, but on a collection of molecules organized in space as a crystal. So you need to crystallize the molecules. Now, in this way, if you are bombarding this thing with X-rays in order to get scattering, yes, you're going to damage some of them, but many of them are not damaged, and those that are in the ordered crystals are producing a coherent scattering patterns, and the other are not. And so in this way, you can solve the problem. You can solve the problem, but with a price. That is, in order to obtain a crystal, you must spend time and money, big efforts, and so on. So it is a huge kind of problem right now. And for example, again, in the case of the COVID virus, the initial step was to try to get some crystals. And it was not completely easy, but it was done. Okay, this is now producing a huge number of results that are collected in data banks in which there are hundreds of thousands of structures deposited, and this is only a portion of what should be done in the forthcoming years. Okay, I think that I concluded this part of my presentation, and I would propose, before opening the door to questions, if the chairwoman is in agreement to continue with the bonus. Is that okay?
Yes, sure. Please.
Thank you very much. All right. Free electron lasers, a short primer, very short. Okay. Now, I will start from the question that was asked before. That is, oops. Sorry. All right. Great. Okay. As I mentioned, there is now a new class or a new generation of synchrotron radiation sources. And the initial question that we can ask is the one that was asked actually by your colleague, that is, you've seen that the synchrotron radiation sources based on storage rings have a number of properties that are somewhat reminiscent of lasers. Strong collimation, high intensity, and so on and so forth. So are they lasers? Well, in order to answer, let's see what is a laser. Take an visible or infrared laser, you find there is an active medium and there is an optical cavity. And the optical cavity is forcing the photons to go back and forth. And there is what is called optical amplification. Now, in the case of storage rings, there is no optical amplification. There are no good mirrors for X-rays because there is no reflection. So you cannot build optical lasers. The answer, as I mentioned before, is negative. These are not lasers. However, we now have lasers. That is, devices that are laser-like because they use an optical amplification process. What's going on? All right, the difference with respect to what we've been doing until now is that up until now, we have been looking at what happened to a single electron emitting radiation. And we neglected the fact that, except for the time structure, that the electrons actually are in bunches. And so we should also look at the collective behavior of electrons in a bunch. And let's do that by going straight to a free electron laser. We need a very long undulator for a reason that will be clear in a few moments. And then we send in the undulator not a single electron, but a bunch, okay? And suppose that it is a high density bunch for a reason that, again, I will explain in a moment, all right? Now, as the bunch enters in the undulator, there will be emission of photons. So there is a wave that is emitted. From this point on, the wave and the bunch are moving. The wave at the speed of light, the bunch at almost the speed of light, they are moving together. And so they are interacting, okay? And see what happens. The interaction is non-neutral. It changes the distribution of electrons in the bunch, and they create a sort of salami with very thin slices of electrons, okay? So there is a confinement of electrons into these micro bunches that have a period equal to the wavelength. And now look at the emission from the electrons that are not distributed in the entire bunch, but confined to the micro bunches. There it is. You can see that the emission is correlated. And so it is an amplification of the initial wave. This is the initial wave, you get amplification. And so you're getting optical amplification. Now, this seems very simple, but actually it's a bit more complicated. Let's have a closer look, but try to keep things understandable. All right. What is that is causing the electrons to be pushed into these slices? The name is fantastic. They're called ponderomotive forces. I could never understand the origin of this name because it's so complicated. And actually, it is a bit complicated if you're looking at all the mechanism. But if you want to extract the important information, you got to think in simple ways, okay? Suppose that this is the emitter wave, okay? The emitter wave can interact with the electrons via the undulator and so on because it has an electric field, for example. We can see here the field of the wave. However, this interaction becomes zero at the nodes because at the nodes, the field is zero and therefore the force must be zero. So no matter what is the complicated mechanism to push the electrons, you know that the accumulation can occur at the nodes, all right? Because the nodes is where there is zero wave, and therefore there is no force anymore. Okay? So that's fantastic, because now we understand this confinement of electrons. Yes or not? Because you see, the problem is that actually this would give you a period that is not one wavelength, but it is 1/2 wavelength. Okay, so we need something more. Once again, this is where the electrons could accumulate. But the other thing is that the accumulation does not occur of all nodes because of the direction of the field. Okay, so the forces do not act in the same direction everywhere. In fact, in a case like this, there is accumulation. In a case like this, there is in fact depletion. Okay, and so, bam, the periodicity is not half wavelength, is one wavelength. Okay, and so this explains how we can do the micro bunching and so on. All right, so how can we build a free electron laser? Therefore, we need some kind of accelerator that is giving us the initial bunch of electrons. We need an ondulator. Once again, I keep saying that it must be very long, but I still did not explain why. I'll do that in a moment. And the electron bunch enters the ondulator. It becomes, once again, micro-shaped, and it emits photons that are also micro-shaped, like the electrons. And so, in this way, we can get a laser mechanism. But what are the necessary ingredients? First of all, we must realize that in order to get X-rays, you need high energy electrons. High energy electrons have a high gamma. And in relativity, there was in the first version a wonderful notion, which is that of longitudinal relativistic mass, which is proportional to the cube of gamma. If you get a high energy electrons, the electrons is no longer a light particle, it's a small stone, okay? And so even if the displacement is very small to get to one of the slices, still it is a heavy particle, so it takes a lot of time. And that is why you need a long ondulator, because otherwise you don't have enough time in order to do the micro bunching. So much about the very long ondulator. It is because of the heavy longitudinal mass. Second, the micro bunching period must be is very short because it's given by the X-ray wavelengths, and therefore the micro bunching gives you a delicate structure which is easily destroyed. Okay, any kind of imperfection or irregularity in the magnets and so on is a killer. And that is why, if you're looking at a typical Wiggler or ondulator, you're not getting a free electron laser, you're getting a Wiggler or an ondulator, all right? So you need special characteristics that are, for example, a very high accuracy of the ondulator and the electron beam. Third, can we use an optical cavity? Once again, no, because there are no mirrors for X-rays, which means that whatever is the amplification, it must work in a single pass. Okay, you cannot get a back and forth, all right? And so this means that you have the need for a very high optical amplification, and therefore you need a high density of electrons, okay? And this has consequences. Okay, and I like to skip these comments and go to the consequences. That is, this is then our electron bunch, which must be a very high density, and therefore it must be very short. The length of the photon pulse is h divided by v, which is h divided by c, and so we are getting very short pulses. We are getting femtosecond pulses. You remember that in the case of storage rings, we got nanoseconds. These pulses are much shorter. And of course, we need to have a small area, and therefore we are going to get a lot of brightness. Good. Now, Coherence. Coherence, especially, is no problem. It is a very good coherence. But in the case of time coherence, there is a problem because we have seen that the optical amplification amplifies the initial waves, and this is the production of the initial waves is a random process, which means that the pulses do not have the same shape. So each pulse emitted by a free electron laser has a different shape, and this broadens the wavelength and therefore screws up the time coherence. How can we solve the problem? Well, we had to avoid using this initial emission and use the long undulator instead to amplify a wave that is produced by another source. Okay, so we have the long undulator, we have an external source. The external source is producing a highly coherent, timely coherent wave with a very good shape, and then you have the amplification. This mechanism has been a dream for many years. Now it has been implemented. And we are getting to the conclusions. This is the reality today. On the side, in Elettra, on the side of the storage ring building, there is a long building in which there is a working seeded, that is with this kind of mechanism, X-ray free electron lasers. So this is no longer a dream, it's reality. A reality with some problems, because what we are doing in this way is that we are packing a tremendous amount of energy in a very short pulse of X-rays, okay? So we are getting a tremendous peak brightness, but with characteristics that cause problems, because we're talking about gigawatts in femtoseconds. This is an unprecedented concentrated power of electromagnetic energy. You send it into a molecule, this is what you do. Okay, that is, you destroy the molecule. Now try to convince the politicians to give you a billion in order to destroy molecules. Cannot do that. However, these things happen in femtoseconds because the pulses have a length of femtoseconds. So what you can do actually, instead of just looking at the final product of the explosion, you can actually look at the structure during all the explosion and then go back and try to reconstruct the initial one, which means now you can do crystallography without crystals. This now starts emerging, and it is a very exciting, a very new technique. So now, these are some examples of what you can study using the X-ray free electron lasers. You see a collection of very short phenomena, okay, and this means that we are opening a new chapter in the synchrotron radiation business. And I'd like to conclude my presentations by noting something which was stressed recently by Joe Storr in California, which I found quite fascinating, because by looking at this tremendous amount of concentrated electromagnetic energy, we are now going back to the foundations of quantum physics. Why so? Well, let me ask you a general question. What is the interference and diffraction of photons? Well, if you are considering them waves, it's very simple, okay? That is using a wave approach, and you understand that. But from quantum mechanics, we know that these are wave and particles. And so, is this the interaction between particles? The answer is no. And this was stressed by Paul Dirac some years, many years ago, okay? He remarked that with the kind of intensities we have, okay, we do not have interference by having different photons that are interacting between them. It is the interaction of a photon with itself. How can you understand that? Very simple. You start lowering the intensity of the photon beam in the apparatus until you, on the average, you only have one photon in the apparatus, and you still have the phenomenon, the diffraction of photons. So it is not the interaction between two photons, It is the interaction of a photon with itself. And this has been the history of quantum physics until now. Why so? Because this is what corresponds to so-called first order of quantum electrodynamics, which is the typical situation for the intensities or the concentration of energy we had until now. But with X-ray seeded free electron lasers, we are going beyond that. Now we are going to the second order, and what was negligible until now becomes important. Good. So thanks for your attention, and thanks for the school organizer for the opportunities. I leave here a small collection of other articles in this series of production if you want to look more in details to any one of these topics. Okay, thank you very much.
We thank you for these fascinating presentations. And there are actually many questions, but we are lack of time. So if you let the participants, they could send you via email their questions, if it is okay for you, because we have to close the recording. We have to close the session now. Can they send the email to you for about?
Absolutely, they're very welcome. Okay, no problem. All right.
Thank you very much, because they are really interested and they have many questions, I think. So then, as we come to the end of the first day, I would like to thank all our speakers and all the participants for their active involvement. I strongly encourage all of you to continue the rest of the week and next week and take full advantage of this expertise gathered. Thank you all again for a very successful first day. I feel that. And I wish you a pleasant evening and look forward to see you tomorrow. Bye-bye.
Bye. Thank you.
Thank you. Bye.
Bye-bye.
Thank you very much.